Now let us observe trajectories of kinematics. Can be defined as path traveled by the body under the influence of an external force. Can be estimated as a function of particle position with time, and trajectory can also be defined as a motion of particle under constant acceleration. Well, let us consider a simple example of a man standing on ground and throwing a stone from his hand. Here, the trajectory follows the kinematic laws of motion. V is equals to u plus at, v square minus u square is 2as, s is equals to ut plus half at square, where s is displacement, u initial velocity, v final velocity, a acceleration, and t time. The parameters of interest in trajectories include longitudinal distance traveled, maximum height reached by the particle, and time taken for the entire trajectory, whereas parameters required for the above calculations involve initial velocity, angle of projection, and acceleration due to gravity. Now let us derive certain equations of trajectories. As we know, the person standing has imparted an initial velocity to the particle he is having, and that enabled the particle to travel on a trajectory. Well, as we know, the particle is given with a velocity, and the velocity is in fact a vector quantity. So this has been given at an angle of theta, which is what we actually assume here in this way, exactly tangential to the point of source. Well, as we know, velocity is a vector, so we can split this entire situation into two forms. One with consideration of horizontal components, and two vertical components. Well, let me consider two situations here. The particle, which is visible here, has been imparted with a velocity of u that is directed at an angle of theta with the horizontal, taking the vertical axis in this way. Now the components of this initial velocity can be split into vertical as well as horizontal directions like this. The horizontal component would be equal to u cos theta, and the vertical component would be equal to u sin theta. So this is how we can actually split the initial velocity into vertical and horizontal components. Similarly, for the particle, there is a constant acceleration acting always towards down, that is g, acceleration due to gravity. And the horizontal component of acceleration to this particle is 0. So taking this under the considerations, now let us go with two component calculations. The first one is horizontal, and here let's go with vertical. And as I said, the initial velocities that are being spread is ux, that is equals to u cos theta, and here uy, that is equals to u sin theta. Well, here I would like to express the time of flight. This would be the first parameter of the trajectory that we derive. Time of flight is equal to the point, is equal to the time, which is exactly the time taken by the particle to reach its initial point. For example, this particle has been thrown up with a velocity of u sin theta. The particle would actually go to the top and come back to its initial point, just considering the horizontal motion of the particle. So here the displacement absorbed by the body is 0. Taking the first law of motion, that is equals to v is equals to u plus at, and second law, that is v square is equals to u square plus 2as. Here a is significant, however s being 0, we have this standard equation of v square is equals to u square, that implies v is equals to minus u. Here we are considering this minus sign because the velocity, initial velocity towards top and towards bottom at the end of the series is on the flip sides, on the opposite sides. So we have to consider the negative mark as it is a vector. So implementing this over here, we have the equation 2u is equals to gt to uy. This is y, this is also y, you have to consider this. That implies time taken is equals to 2uy by g, that is equals to 2u sine theta by g. So this is the first equation, that is the time of flight that we have derived here. Now let us go what exactly is happening on the horizontal side. On the horizontal side, if we want to calculate the range, it is equal to s on the third equation of the laws of motion, that is equals to ut plus half at square. Well, we already know that acceleration on the horizontal side is 0. Thus, when we equate the same formula, it would be s is equals to ut, where u is x component of u. That implies r, or s as called in this equation, is u cos theta into time. This time can be brought from this equation. That implies r is equals to u cos theta into 2u sin theta by g. That is equals to u square sin 2 theta by g. This is how the equations can be molded down. Now the third parameter which we are very interested in calculating is the height reached. To be honest, if we just calculate a particle thrown at a horizontal curve, velocity component of u sin theta, going up and falling down, at the topmost point its final velocity is considered 0. So with the equation v is equals to u plus at, which was the first formula, we have the equation u sin theta, u sin theta by g is equals to the time of ascent, which is exactly equal to the half of total time of flight. This reminds me to tell you that time of ascent is equals to time of descent. It's equally spread. So with this, if we actually import the same equation on the second law of motion, that is v square minus u square is equals to 2gs, that implies s is equals to u square by 2g, where v is actually 0. That implies s, that is height maximum, is equal to u square sin square theta by 2g, because in the entire expression we are actually dealing with the component uy square, that is u square sin square theta by 2g. This is actually the maximum height reached by the particle. Well, this is how the fundamentals of a trajectory can be made, where a person throwing a particular stone or any particle under a trajectory, when it reaches to almost same height as the initial height. The range is equal to 2u sine theta cos theta by g. The height reached by the particle is u square sine square theta by 2g, and the time of the entire flight is 2u sine theta by g. So this ends the discussion on the trajectories right here.